Hello to everyone, I'm Roveda, and today I'm going to introduce the work that has been done in the paper Design of an Impact Force Switching Controller that has been accepted to IRD in 2021. The authors are Roveda, Daniele Riva, Giuseppe Bucca, and Dario Piga. Intelligent interaction control is required in many fields of application, such as manufacturing, space robotics, and so on, in which different operative situations have to be faced with different controllers. Being able to switch between optimized controllers based on specific operative conditions is indeed of extreme importance to maximize the task performance. The main aim of the proposed paper is therefore the definition of the OSIF controller, an optimal switching impact force controller capable to switch from optimal impact control to optimal force control and vice versa, on the basis of the current task phase. In this slide, we can see the main control schema related to the OSIF controller. We can highlight the low-level controller that is composed by a Cartesian impedance control and an inner joint position controller. And we can highlight the high-level controller that is composed by the optimal impact control, the optimal force control, a fuzzy logic capable to switch among these two high-level controllers, and an adaptive impedance Cartesian impedance controller block in order to update the Cartesian impedance control parameters during the task execution. We can also highlight an extended Kammal filter that has been used in order to estimate the external interaction in order to apply the proposed control schema to a sensorless manipulator. Here we detail the extended Kammal filter results. In particular, we can highlight the estimation of the extended Kammal filter with respect to both forces and torques, with respect to the measurements provided by the adopted robot that is a Panda Mica Frank robot. And as we can see, we are able to achieve a good accuracy in the estimation, and therefore we are able to implement the inner Cartesian impedance controller based on this estimation. Here we would like to highlight the results achieved by the optimal impact control. So here what we have is the robot controlled only with the optimal impact control strategy, capable to achieve an interaction with the surrounding environment without force overshoots. And here we highlight the achieved interaction forces, in which we can see the maximum force that has been defined for the controller and the measured force. And we can see that the measured force and the estimated one are always below the defined threshold. For the first experiment, we defined the threshold of 10 newtons. For the second experiment, we defined the threshold of 20 newtons. Finally, we tested the complete OSIF controller, and we can see in a probing task that we are able to achieve the tracking of a reference force with limited force overshoots. On the left, we applied the OSIF controller to a sensorless manipulator, while on the right side, we applied the OSIF controller on a sensor-based manipulator. And in both the cases, we can see that we are able to track the reference force. In the second case, we can highlight the avoidance of any force overshoot. Finally, we considered an advanced assembly task. And here, what we can highlight is the capability of the controller to switch based on the task phase. In this trial, we are able to achieve a stable interaction between the robot and the environment with only one transition from non-contact to contact. While in the second trial, we can see that the robot is capable to, the controller is capable to switch multiple times between impact and force controller.